Rotational kinematics, which, as I have told you, is a very important part of this course. We have done quite a bit of work on all the other things that we needed to do. I will continue to give you problems on work and energy because the concepts of work and energy are going to be used through the chapters that we are going to be doing now and probably beyond as well. And also in one or two, it will be used. Now, if you have done the homeworks the way they were supposed to be done, the set that just got completed yesterday, the whole idea behind the stuff I assigned was to see how to work with the Work-Energy Theorem. It is a very powerful theorem. I don't know if you guys thought much about the problem where the mass comes down a weird shaped slide and hits a spring. When a mass comes down such a strange shaped slide like a parabola, if you're trying to estimate the friction force, it's not easy because the normal force as it's coming down is changing continuously. So there is no way in which you can actually estimate the friction force without doing calculus. But that problem was set up to show you that there is an approximate way by which you can actually estimate this extremely complex friction force by simply finding out how much the spring got compressed, which was the other end. Can you turn off your phone? That does mean that you shouldn't have your phone next to you, because there are people at the back who I pardoned last time. You had your phone next to you as you were taking your quizzes. In the previous years, if your phone is next to you, I've basically canceled your quiz. So just because I'm being nice, don't abuse me. All right, so back to stuff. So basically, the work-energy theorem gives you a fantastic way of calculating the frictional loss in a problem. So think about that problem, go back to it if you can, and do some post-mortem. I'm going to throw some more problems like that at you as we go along. The homework set 9 is running a little late, partly because I'm a bit overwhelmed. But what I'm going to do is I'm going to assign 3 problems right now, probably by late tonight, early tomorrow. And I'm going to assign 3 more problems for homework set 9 itself that will probably be coming around late Wednesday, early Thursday. So that way I can get you the kind of practice you need to get you prepared. But I'm simply unable to do all the problems that I'm trying to make up in one go so far, okay? So so just get started on them as I give them to you. In the normal years, since this time we're making a new set altogether, I'm assigning problems on a weekly basis. Normally I would assign problems Sunday, they're due Wednesday. I'd assign problem Wednesday, they're due Sunday. So they're like two problem sets a week. You guys are having it a little easier because we are making problems, but you're also getting different kind of problems, so it's okay. But this week will be a little weird. All right, so on to rotating objects, or I would call rotational kinematics, okay? So just like we did kinematics before, this is rotational kinematics. So what do I mean by rotational kinematics? Well, basically what it is that you can start with the picture of a wheel that is turning about some axis. So this wheel is not moving in the sense that it's not going sideways or up or down, but this wheel is turning on its own axis. Let's say the axis is the center. It doesn't have to be the center, but let's say the axis is at the center, and let's say this wheel is turning. How do we analyze these problems is where we start today. So it turns out that you first have to worry about the radius r of this. And then you say, well, over some time delta t, let's say this thing turns by some sliver of an angle, which we shall call delta theta, okay? So delta theta, this turn happens in delta t, which is a small amount of time, small interval of time. So we already know for a while now that the speed, if I measured the speed anywhere at the edge, let's say, call it point A or call it point B, then the speed there would be omega times r, where omega is the angular speed. Just to remind you, omega by definition is 2 pi over t, right? And just so that you never forget this formula, remember that this is speed, and speed is distance over time, and distance over time basically is 2 pi r, which is the circumference, over the period t. So that's where it comes from, because 2 pi over t, this piece here is omega, so this is omega r. So that's how this thing came to life, just so that you don't forget these kind of things. So now what we're going to do is we are going to essentially talk about the fact that omega itself can be defined as delta theta over delta t, because it really is what angle is being traveled over time, delta t. So now what we'll do is we will say that unlike before, omega is not a constant. So in the past, where we have done uniform circular motion, we have assumed that this omega is a constant. But now we are relaxing that assumption. We are taking away that assumption, and we are saying that omega doesn't have to be a constant. What does it mean in real life? In real life, it means that as a wheel turns, the wheel can be speeding up or slowing down. Okay? Then your omega no longer will be a constant. Omega will vary as a function of time. So now you see, I can actually define some kind of an acceleration regarding omega, and this acceleration is denoted by alpha. And alpha is actually something very simple. Just like omega, just like we have related omega to theta, alpha is defined as how much change in omega transpires, so delta of omega over some very small interval of time, delta of t, and this thing is called angular acceleration. Just like you have acceleration A in linear motion or acceleration g in linear motion, you are now talking about angular acceleration, which has to do with this rotational kinematics problem. Furthermore, we will try to make our life quite simple for now, but before we go there, let me just point out a few things. So one can now think about, just like we have a speed v, one can actually think about something called a tangential acceleration. So this is an angular acceleration, this is a tangential acceleration, and the tangential acceleration, in analogy with v equal to r omega, is a equal to alpha r or r alpha. So all of this is not a surprise, because if you think about the units here, this is 1 over time, but omega itself is 1 over time. So therefore the units here would be 1 over time squared, and therefore 1 over second squared. Right. That's the unit of omega. Yes?
What is the acceleration in TAN?
TAN. So, okay, so this is the tangential acceleration. So I'm coming to that. So if you now go back to our wheel, now you see this rotation can speed up or slow down, right? And so therefore there is an acceleration attached to it. This acceleration is what we call alpha, which is the angular acceleration. Nothing but delta omega over delta t. However, this angular acceleration alpha can be related to a linear acceleration alpha. All right? How do you do that? Well, you have to find something linear, in this case r. Why would we do that? Well, it turns out that you can also associate an acceleration with any point here, let's say. just because this thing is going faster and faster or slower and slower. You can also associate something that we will call a tangential acceleration. So this, for example, if it's rotating that way and it's speeding up, your tangential acceleration may be a vector this way. This is your tangential acceleration. Okay? So contrast that with what you have dealt with so far, which is your centripetal acceleration. Now that hasn't gone away. Your centripetal acceleration is alive and well. So your centripetal acceleration on the other hand is that way, towards the center, right? So this is AC, and we have known AC for a long time, and this quantity we already know is v squared over r, right? You have been dealing with it for a long time. So centripetal acceleration AC is v squared over r, but tangential acceleration is alpha times r, where alpha directly ties into how the rotation is speeding up or slowing down. So therefore, the actual acceleration that this point will have will be the vector sum of this acceleration and that acceleration, and depending upon how strong they are, it will be in some direction like that. So the actual acceleration that you would experience in a rotationally in a rotating disk, for example, is therefore quite complicated. It has both the centripetal acceleration as well as the tangential acceleration playing a role. So very simply put, if I actually want to compute the acceleration at some point A, this acceleration would be AC squared plus A tan squared square root. And this would be the magnitude of the acceleration that one would have, that acceleration that I have drawn. And in this case, that A is here, this A. Okay. All right. So I've told you about theta, about omega, and about alpha. Let me tell you something else, which is very, very interesting, I think. When you did kinematics, in the very beginning of this class, we dealt with scenarios where acceleration A was constant. That's what we did. When A started varying, we started to play with Newton's laws, because that's what related A to force, acceleration to force, and we learned to deal with force, which means we learn to deal with what happens when acceleration varies. So right now, though, let's go back to that stuff that we did quite a while ago. And you remember in kinematics, we talked about displacement x. We talked about velocity v. We talked about acceleration a or g. Now, on the other hand, we are doing something very similar, which is rotational kinematics. And now we will assume, for simplicity, for now at least, that instead of acceleration being constant, angular acceleration alpha is going to be constant. That means it's the speeding up or slowing down of the rotational motion is constant. And it turns out that we realize that v is r omega. And we also realize that a is r alpha. And it's easy to see that we can relate distance to x equal to r theta. You just multiply that with the radius r. So there is a one-to-one correspondence between rotational kinematics and kinematics that you have done before, which means necessarily that the kinematic formulas that we have used, for example, we use the formula x equals, let's say, x minus x0, or in general, x equal to some initial displacement x0 plus, I don't know what I use, v0 t plus half acceleration times square, right? We use that. What can we do with it in the rotational kinematics problem? Well, it turns out we can write theta, because everything is You see, it's theta, omega, and alpha, just like x, v, and a. But to relate to x, v, and a, you've got to multiply with r. That also makes them dimensionally correct. So I can write this without really doing anything else as theta equals theta 0. The analog of v0 is omega 0, some initial angular speed, plus 1/2 alpha t squared. So the first formula of rotational kinematics pops right out by analogy. We can think about v being v0, initial velocity, plus acceleration times time. That was one of the formulas that we worked with. Well, correspondingly here, for v we have omega, right? So omega would be omega 0 plus angular acceleration times time. You get the picture. So in other words, I don't have to do anything. I know everything. I just have to make sure that I attach the right equations with the right quantities. We know, for example, that v squared is v0 squared plus twice acceleration times x minus x naught. That was another important formula that did not involve time. So right now what we can do is we can directly write omega squared is omega 0 squared plus twice alpha theta minus theta naught. So I'm going to assign you problems in the set that's coming up based upon this kind of rotational kinematics. So anyway, you get the picture. Whatever equation that you need, you can directly construct with the substitution of the appropriate variables. You just work it out. Okay? Any questions so far? All right. So, but there is a big thing that we need to worry about. Remember I told you that we have been replacing objects by their masses in one point. Concentrated in one point. It doesn't seem like a big deal once we start doing it, we get used to it. So we can say, well, we have a block here, and this block is sitting on a table, and this block has a certain mass m. Intuitively, we assume that we can replace this mass by a single mass point at what would be the center of mass of this point, of this object. That's what we have been doing from the very beginning until now. But we cannot do that really anymore when you have rotating solid objects. Life changes dramatically now. So what really happens and why not? Well, let's look at it. One of the things that we learned is if this object is moving with a velocity v, let's say, then we can calculate its kinetic energy, and the kinetic energy would be 1/2 its mass times the velocity v squared. We know that, right? So we know how to calculate kinetic energy. And kinetic energy has to do with how much energy the object carries by virtue of its motion. That's what kinetic energy is. So here you see we have our wheel that's turning. Okay? Our wheel is turning. So what would be its kinetic energy? Clearly it will have kinetic energy because if you look at a turning wheel, it's easy to see that it possesses energy just because things are going around. It should have energy. So what is its energy? Well, one can make it a very simple argument and say, well, whatever this object is, this object can be thought of as made out of tiny blocks of mass somehow. And if I could take into account all these masses together, multiply the masses with their velocity squared and multiply by half, I should be able to get the total kinetic energy of this wheel. So in other words, the kinetic energy of this wheel can then be thought of as sum over I that means all these particles, 1/2 mi, so masses of each of these whatever cubes that we have, times the velocity of the cube squared, right? That's what it should be. Why not? Because that's the definition of kinetic energy. But it turns out that things get a little bit more difficult when you're looking at circular motion or rotational motion. Why? Because you see, the velocity of this guy and the velocity of this guy and the velocity of that guy, even if you have the same omega, would not be the same, because v is r omega. So the distance from the axis, in this case the axis, let's say, is here, matters. So therefore this v has a distance involved. So therefore it's not quite as simple as we thought. Now we certainly can get rid of the half. That's a very benign quantity. We can now write whatever is inside, the sum that is, mass I, mass of point I, mass at point I, whatever you want to call it. And then this guy I can call omega Ri, whatever the distance of this block is from the axis, square. All right, I can call that. Now omega is common to everything, unless of course you are dealing with jello. Because it's a solid object, the delta theta over delta t should be the same no matter where you are on this disk, let's say. But if the disk was made out of something very soft, like some jello or some whatever hair gel or something like that, and you were rotating that, it will turn out that you wouldn't have done what I have done, because what I have done here is I have said that the angular speed omega is the same everywhere. But it turns out angular speed omega will not be the same everywhere if it's a floppy object, that is. But this is a rigid object. So we should therefore be careful and say that we are doing rotational kinematics of rigid objects. So we need some specification. In fact, we will not do rotational kinematics of non-rigid objects in this course. It's far more difficult to deal with non-rigid objects. All right, so let's go back to what we were doing. We were calculating the kinetic energy of that rotating wheel, and we have come to the conclusion that half can come out. Omega is common to everybody, so I can take omega out. So I can throw an omega square out. Then inside, I'm left with m sub I, r sub I squared. And let's put this whole thing in a bracket. So now let's think about this a little bit. So suppose for that disk through the with an axis through the center, so I'll draw a smaller disk. I'm running out of space. So this is my disk with an axis through the center. This mi pertains to every little piece of mass I can construct wherever. And of course I have to sum up all these masses to be able to describe the whole object. Now, you were probably wondering, what an insane way of doing science. You have a disk and you're breaking this enormous disk up, circular disk obviously, into little blocks, and then you actually want to sum up the masses of every little block? That's crazy. It is crazy. Well, the craziness was solved by Newton and Leibniz a long time back, because you can use calculus to do that. We won't be using calculus, so we won't be calculating these quantities explicitly by hand, but in a 107 course, for example, we actually do quite a bit of that in class. So it is actually possible, believe it or not, to calculate this quantity. What is interesting here is the fact that each of them have different RIs, because they're at different locations. So what this means is, if I take the same disk, but instead of putting the axis to the middle, I put the axis here, then of course the disk would be rotating in a different way. So in other words, this is the axis and this disk is rotating, right? So it's going to be very uneven. And now you see the RIs would be completely altered even if the MIs are not, because now these RIs are going to be different. So what I'm trying to tell you is that for a rigid object such as this, not only does the detail of the rigid object now become important, where the axis is also becomes equally important. You would never drive a car where the centers of your front and rear wheels are not connected. Why not? Have you thought about it? You would drive a car, right? You drive a car or a bus or whatever where the centers of the wheels are connected. What would happen? Why would you not do, what is the problem if I want to drive a car where the wheels are connected here? Why is that not going to be a good thing to do, you think? What is the problem with that? I'm not crazy, I'm asking you a question. I want to drive a car. Yes?
It's not centered, so it's going to produce a very bumpy ride.
Yeah, but I'm okay with bumpy rides. So what if I have a bumpy ride? There is another problem with it. Come on. I'm okay with bumpy rides. Yes?
Is it because the effective radius is much larger with that wheel setup than
Well, you have the right idea. It is not the effective radius per se. It will turn out that this quantity, remember, kinetic energy is 1/2 omega squared times this quantity. So now if you have an axis at one extreme end in an object which is quite symmetric like that, instead of having the middle, it will turn out that this quantity will actually get jacked up in value, which is what you are roughly trying to say by effective radius. Because if you think about it, if the axis is through here, the region around here is tiny, right? But there is a lot of stuff outside, quite far away, as opposed to here where everything is symmetrically located. So it will turn out that this one actually will have a higher value of this quantity. And because it will have a higher value of this quantity, it will be dissipating more energy. It will be carrying more energy, it will be dissipating more energy, and it will be an extremely inefficient vehicle to drive. So even if you're completely okay with bumpy rides and you sit on a, nice, cushy seat, maybe you won't even feel it, all the shock is absorbed, but energetically it will be a disaster because you'll be wasting a lot of energy. By the way, this quantity here has a name, and we will now look into this. It's denoted by I, and this I is called moment of inertia. It's called moment of inertia. Moment of inertia, by the way, is the analog of mass in rotational motion. Analog of mass in rotational motion. That's what moment of inertia is. So what I'm trying to tell you then is that we can replace this quantity as 1/2 I omega squared. So instead of having 1/2 mv squared for a mass, for a point mass, as we have so far, we now have 1/2 I omega squared. So the equation and the ball game changes on you because now you have to worry about this I. What does this I do for us? Like I said, if you have an object, you not only need to worry about the shape of the object. For example, you can have a rod, you can have a triangle, you can have some weird shaped object. Not only do you have to worry about the shape of the object because that influences your calculation of I, the moment of inertia, but you also have to worry about where the axis is located, because if the axis here is in the middle, you'll get one value of I. But if the axis is located here, or here, or here, or here, it doesn't matter where you place it. The fact is that your value of I will come out different. So therefore, rotational kinematics and rotational dynamics is in many ways infinitely more complicated than what you have done so far, which is why we do it much later. So now the question is, how the hell will you calculate I? Well, luckily, in 101, the I calculation is really not emphasized because it is pretty much impossible to do it easily without calculus. So let me give you some basic I's. Okay, I'm going to give you the I's in your calculations, so I won't insist that you know these I's. So this, for example, is a disk, or this, for example, is a cylinder. A disk, therefore, is no different than a cylinder, excepting that the width of the cylinder is small, much smaller compared to the radius. So it turns out that for a quantity like this, as long as you are talking about a motion through the center, the moment of inertia I is 1/2 its total mass times the radius r squared, as long as you're talking about axis to the center. If you're not talking about axis to the center, you'll have to calculate what the moment of inertia is, and I'll come to that in a minute, maybe in more than a minute. So it turns out then that for a disk, it's very, very simple, and it's 1/2 mr squared. Like I said, the shape matters. Now you can ask, for example, what is the moment of inertia of Earth, assuming that Earth is a sphere, which it is not, but approximately it is a sphere, going around in its axis, which is tilted in some angle, 22.5 degrees or so, whatever. Not a very good sphere I have drawn, so forgive my artistic talents this morning, but it's going around and it's a sphere. So for a sphere, the moment of inertia I, if you could actually calculate this, and it's easy to calculate using a little bit of calculus, is twice mr squared. 2/5 mr squared. Okay. So you get all kinds of numbers, all kinds of very, very interesting numbers when you actually start to do these moment of inertia calculations. For a rod like this, if you have an axis to the middle, then it turns out that the moment of inertia I is 1/12 mass times L squared, where L is the length here. 1/12 ml squared. So if you look at your book, there is actually a table that describes what these various values of moment of inertia are for various shaped objects. And so at a given problem, if I don't give you the actual formula for the moment of inertia, what you do is you go look up the table that has the stuff. There is one more thing I want to say regarding this topic, and that's what happens when the axis is shifted. And this is called the parallel axis theorem. This is a simple one to use. The idea of a parallel axis theorem is that suppose I find out the moment of inertia of this disk from to the center. Suppose I do that. I already told you that the moment of inertia of a disk to the center, let's call it IC, is 1/2 its mass times the radius r squared. I already told you that. The question now is that if I now change the position of the axis through which it's rotating to here, let's say, or here, some other point, then how will I calculate the moment of inertia of the same object about that axis? It turns out that, let's say in this case, the distance between these two is d. Okay? So then it will turn out the moment of inertia I about this point is going to be the moment of inertia about the center, that's very important, plus it will turn out it will be the mass of the object times the distance d squared. What is the distance? The distance is the distance between the 2 points. in this case, the original axis and the new axis. So the parallel axis theorem therefore allows you to calculate the moment of inertia about some other point if you know the moment of inertia about the center. Now the advantage of it is that it is much easier to calculate moment of inertia about the center. So if you always do moment of inertia calculation about the center, and then you just use parallel axis theorem to go to some other point. Let me now switch gears. Let me ask you some questions. Suppose I take something like I take the idea of a bicycle. I take two wheels and I connect the two wheels. Okay? So this guy is turning and this guy is also turning. And these two wheels are obviously connected by some kind of a cord or chain or band or whatever. And let me just say that the speed with which this thing is moving as the wheels turn is v. Okay? So the question is, what does it tell us about the rotations of this object and that object? This, by the way, is what you actually have in your bicycle, right? In your bicycle, you have two wheels which have two different radii. In fact, the small one is actually tied to it's attached to the rear wheel, the big wheel, and it turns out that this is how you pedal one of them, and then the other one turns. It turns out that here, let's say the radius of this guy is r1, and the radius of that guy is r2. So it turns out that since v is common to both, v must be omega 1 r1, because v is r omega, we know, and also equal to omega 2 r2. So therefore, if I know r1 and r2, I can calculate omega 1 and omega 2 and vice versa. So this is a principle that has been long used in engineering to solve a great many problems regarding machines, including bicycles, this, that. The whole gear system is based upon this very same simple idea. So I've given you a problem on this. You can obviously see that if you make one of the wheels smaller, then what it really means is that your r value goes down. But since v is fixed, that necessarily means that your angular frequency goes up. In other words, if you want to have very high frequency rotation with a system like this, all you need to do is shrink your r appropriately. So let me now try and show you a relatively straightforward problem. I think some of you came in late, sitting at the back. I will not give you quizzes. So if you want to leave, you are welcome to leave. So let us say I actually have a disk here, and I have a cord tied to this disk. And let's say part of the cord is sticking out, and I take this cord and I pull it. Okay? So I pull it with some force F. And let us say that the distance by which I translate the edge of this cord is some distance x. So one of the things that you immediately see is that the work done W is force times distance is F times x. Force is that way, displacement is that way. It's a cosine of 0. I don't really have to worry about having to multiply with signs and so on and so forth. Now, work-energy theorem tells us that work done is change in kinetic energy, okay, delta K. I'm circling back to something that we have discussed quite a bit, which is work-energy theorem, and I'm circling back to that. So work-energy theorem, therefore, Fx is delta k. But what is it that I am supposed to associate this delta k with? Now imagine you have a wheel like this. Imagine that you have a yo-yo, for example, and you are pulling the yo-yo is fixed, okay? Yo-yo is fixed about an axis. You're pulling the string. What happens to the yo-yo? I'm not going to give you the answer. What happens to the yo-yo? Huh? It spins. If something spins, does it have energy?
Yes.
All right. So what kind of energy will it have? Don't do this to me. I'm asking you a question you can answer. You don't have to be rude. What kind of energy does it have? Huh? Kinetic energy. How would you calculate that in this case? You don't have to say, anybody can say, but how do you calculate that? MGH? Come on. How do you calculate the kinetic energy? What have we been doing for a while? How do you calculate kinetic energy of a rotating wheel? Yes. Huh? Yes, but then we whittled it down to something simpler, right? Come on. Yes.
Like 1/2 the mass times the angular velocity.
Mass? No, not mass. We have gotten rid of mass. What is it that we have instead? I. We have the moment of inertia. So now you see, it's very simple. That's why I've been pushing you guys. It's very, very simple. There's no reason why you can't do it. So if this was originally at rest, the kinetic energy would essentially be 1/2 times I times whatever highest angular frequency that it'll achieve, omega f squared. Because the work's been done, I've pulled it. And it's going to start to go faster and faster, spin faster and faster. And therefore it's going to be 1/2 I omega final squared. But I'm not done yet, because I know it's a disk. And let's say this disk has a mass m and it has a radius r, right? So therefore this is going to be 1/2 times 1/2 mr squared omega f squared. So therefore it's going to be 1/4 mr squared omega final squared. So therefore if I want to calculate omega final, its numerical value, and this omega final is going to be f times x, which is my w, multiplied by 4 and divided by mr squared, and this is square rooted because there is a square there. All right. So it seems like a very simple problem, but when you actually have to work it out, the tiers of understanding that you need is not that simple. So it's quite a bit of work. But the basic idea is very, very simple. We are leveraging work-energy theorem here for our fairly complex dynamical problem, and we are saying that the work done in pulling this is force times distance, and then what we do is say that's kinetic energy gain. Kinetic energy is 1/2 I omega squared, and I just put in I here, and omega final square. I know what I is because it's a disk, and therefore here the disk physics goes in, and then you have a formula for the final angular speed. let us now add something to a problem that we really have touched upon earlier. You similarly have a wheel, and in this case it's like a pulley, let's say, attached to some surface here. Okay. And let's say some string is wound around it, and there is some mass here at the end of the string. So let's also say that this is the ground level, and the distance from here to the ground level is h. So this mass starts off here and slowly comes down. Very simple problem. The pulley is unwinding and the mass is descending. So let's say the mass of this disk is big M and the mass of the small disk is small m. You obviously have gravity acting downward, and therefore if I want to write the energy of the system, the total energy of the system when it started. So originally when it started, the mass was say here and it's coming down. Okay, so that's the picture. The total energy of the system initially was small m times g times h, that's potential energy, plus big M, which is this wheel here, times g times also h. Okay? Now let's say it has descended to some point here, and as it has descended, it's also moving with some velocity v. And as it's moving, this thing is turning as well with some angular speed omega. And whenever you think of omega, the immediate thing that you should simultaneously think about is that v is omega r, which means that this rotational speed omega is actually related to this v here. If you don't make that association, you will simply not be able to solve these problems at all. Okay? It's important that you make these associations to be able to solve this problem. We will later call it the no slipping condition. I'll withhold a discussion of the no slipping condition for now. We'll discuss it on Thursday. But remember, whenever I have an omega, in this case omega for this and something connected to this which is moving, then v is r omega. We actually used it in that problem as well. So in this case v is r omega, so therefore the total energy, so this is total energy when this is here. Let's call it position 1 and let's call this position 2. The total energy, this is the total energy at 1. Same total energy at 2. Since total energy is the same, I can equate that to, let's call this height h prime, right? So now I have mg h prime, that's the potential energy of the mass. The mass is moving downward, so I have a half mv squared. Then I have the original potential energy because the wheel is where it is, mgh, that doesn't change, but the wheel is turning, so I have a half I omega squared. So there are all these four pieces that are now coming in. This is why I've told you guys time and again that we are entering a very, very difficult part of this class. This is the part where the learning curve really goes up. So I'm telling you also that v is r omega. So therefore I should be able to write this as mg h prime plus 1/2 mv square plus big mgh plus 1/2 I, but now omega can be written as v squared over r squared. Then at least I have v everywhere. And it turns out that at position C, just as this mass is about to hit the ground, the total energy would be 1/2 mv final squared. It's a different velocity now. Velocity is going up. Its potential energy is gone because it's at zero height. The potential energy of the actual disk itself remains, and the disk also keeps turning, but now it attains its highest angular speed. So I omega final squared, which is same as v final squared over r squared. So one of the points I want you to note in this calculation is that this mgh piece doesn't really help or hurt us in any way. So you can ignore it because that mass is not really going up or coming down. So that just sets a number for the potential energy that doesn't really change throughout the problem. So the fact that that disk is sitting out there, the potential energy of this disk itself is not that important in this calculation. There's nothing wrong in keeping it. You probably should keep it just so that you can avoid making an unnecessary mistake, but it turns out that that potential energy term is the same everywhere, so it doesn't matter. So why am I doing this for you instead of doing it as a regular problem? Because before I do it as a regular problem, like I might assign in the homework or in an exam, it is very important to first understand how is it that you set up these energies. And that's exactly what I was trying to show you. So let us now try to calculate what goes on at point 1 and point 3. Let's call it point 3. This is at the base. So I can basically say that mgh, which is what was going on initially. I'm not going to take the big mgh because as I have convinced myself that big mgh continues everywhere. So I can just subtract it off. So small mgh, and I'm relating it to state 3 as this mass is coming down. So that's going to be 1/2 m v final squared. Again, I ignore mgh. Plus 1/2 I omega final squared, but 1/2, this is a disk, so it's 1/2 mr squared, where r is the disk radius. And omega final squared is v final squared over r squared by the very same argument I made in converting with v equal to r omega, the quote-unquote no slipping condition, as I said. So now you see, happily this r squared goes away, and I'm left with 1/2 m v final squared, right? This is going to be 1/4. And this mass is different. This is small m, this is big M, v final squared. Okay. Any questions so far? All right. What is my goal? My goal is to calculate v final at this point. So what is v final? Well, I can essentially let me just simplify things a little bit first before I calculate v final. So here I can take v final square outside because it belongs to both terms. I have 1/2 m, small m that is, and then I have 1/4 big M, right? So what I can do is I can actually take out this half outside and make this 1/4 into a half. That looks a little nicer. So now I can write v final square. V final square is 2 mgh divided by small m plus 1/2 big M. So this is very different than what we had before when you had v final square is 2gh, which is what we have been seeing for free falls for a very long time. So as you can see that the v final here, when you have this massive pulley, is very different from a free fall problem that we have now done for a long time. Why is it? Well, if you look at it, the physics itself is far richer because we have the mass of this wheel coming into the picture. Because see, if this mass of the wheel big M goes up, in other words, you have a more massive, larger wheel, what happens? The denominator goes up, which means that your final velocity associated with the mass hitting the ground actually does go down. And this is indeed something that we know is intuitively dated, right? Because if you are turning a big wheel to lower a bucket, for example, heavier the wheel, larger the wheel, the slower the bucket will descend. We know that very well from real life intuition. So therefore, this is a problem where you can actually calculate how this thing will change. So the final formula for V final, of course, is you just put it as a power of half. So I've essentially completed the rotational kinematics chapter so far. Rotational kinematics, as I said, is a difficult chapter. It comes with multiple levels of challenges. And Thursday, I will do a little bit more of it, but really pivot to the more difficult of the two chapters we are doing, which is rotational dynamics, and we'll start with the concept of torque. One of the things that you guys are not doing is you are not using the worked out example problems in the textbook quite the way that you should be. In fact, I think most of you are not, which is one reason why the amount of problems you are seeing as you go along is rather low, because we can only do so much on the board or in the homework assignments. I know you're all busy, everybody is busy, but if you want to do well, if you want to be prepared, I really, really want you to be on those problems. Okay? So with that, let's go to the quiz. People who came in